It is now time for a mini lesson on light. This one's a little longer than the hybridization video lesson that you saw or will be seeing. And I'm going to cover it briefly, let you spend some time looking at the notes too, at some example problems, but because it's not a heavily tested topic, but it is definitely a possibility that we're going to see it on the test. So this little diagram you have on your notes just kind of goes through some different thoughts in terms of the electromagnetic spectrum, lets you kind of get an idea of what the sizes of these wavelengths are. Obviously right here in this little teeny tiny area is where we see visible color. So obviously what we see as colors, are what we think of as our most common wavelength, really is not. I mean, look at all of the other possibilities and how small visible light is on the spectrum. What you really need to be familiar with and understand is how wavelength and frequency and energy of light all interrelate with each other. So that's what we're going to take a look at here. You can see here this first statement says all electromagnetic radiation can be thought of as waves that are defined by their wavelength and their frequency. And you see the symbols here for wavelength and for frequency right here. Okay, so really what we're thinking about is how wavelength and frequency are related to these waves. So you first need to understand what a wavelength is. So start with wavelength. Definition of wavelength is the distance between two repeating points on a sine wave. So this is a sine wave. Wavelength would be from, say, the top of one, and then you go all the way to the top of the next one. Okay, or you can see here they started sort of in the middle of one or at the midpoint, and then went all the way, so here, all the way to the midpoint of this one. So either way, they both show the same representation of that wavelength. Now a frequency is the number of waves that can pass a point in space in each second. So you can't show that on a diagram because it's going to be how often the wavelength passes a certain point. If you've ever been driving in a car and counting the seconds between you and the car in front of you, you can use a point of reference. How many seconds goes by before you pass that point, or how many cars go by, or whatever the case may be. So it's about how many times that wave passes a point per second. So if this thing was moving and going along, we would see how many waves pass, say, this point right here per second, and that would give you the frequency. Okay, now those two things are related to each other, and this statement up here at the top of your paper is a very important one. Let's see if I can get my highlighter actually working. Of course not. So we'll use this highlighter. So right here it says the wavelength and frequency are inversely proportional to each other. Okay, so that means when you have a long wavelength, you're going to have a short frequency. When you have a short wavelength, you're going to have a high frequency. And you can see that here in this graph. Okay, inversely proportional to each other. So the equation that you might be asked to use is this equation. So you have your wavelength times your frequency equals C. And C is not concentration. We just did Beer's law that had a little c in it. When you're talking about light, C is the speed of light, which is 3.0 times 10 to the 8th meters per second. That's the speed of light. All of these values that I have yellowed here on your paper, highlighted in yellow, they are all on the reference sheet. Okay, so you will have this equation that relates frequency and wavelength, and then to C, to the speed of light, and you'll also have the value of the speed of light. Okay, now those two concepts, so you can use this to find either one, because the speed of light is constant, so you can, as long as you have the frequency, you can find the wavelength and vice versa. That also relates to energy. So if you look at this statement, it says energy of electromagnetic waves is proportional to the frequency and inversely proportional to the wavelength. So energy is proportional or directly related to frequency and indirectly related to the wavelength, as shown in this equation here. Now this equation does have a different constant, a new constant in it. This H value is called Planck's constant, and it has a value of 6.63 times 10 to the negative 34th joules times seconds. And that value, notice, is yellow because they also give you that value on the AP test. We know this right here is the frequency. If we don't have the frequency given to us in the problem, but we're asked to calculate energy, if we're given wavelength, right here you can see that if you take the speed of light times the wavelength, you get the frequency, as we saw in this equation up here. Right? If we want to solve for V, we divide the lambda over to the other side. And the yellow version of the equation's given. You could always be using both of these equations. So just a couple of equations to kind of understand what the variables are. And if you understand the variables, then the equations are very straightforward as long as you know what they are. By the way, on the test, they actually show you these variables. They show you this as wavelength and this as frequency. So if you get that example of the equation sheet I gave you out of your notebook, you'll see it's all listed there for you. So it just really is a matter of knowing to look for that information when you get a problem. Okay, so like for example, here's a problem. It says, what are the frequency and the energy of blue light that has a wavelength of 400 nm, which is nanometers, and then they tell you what a nanometer is here. So first thing we want to do is get it into meters, because if you remember, your speed of light up here is in meters per second. So we want it to be in meters. So I get it into meters. Then once I have it in meters, so that's my wavelength. Okay, that's my wavelength. I plug that in for my wavelength. I plug in 3 times 10 to the 8. That's a given. That's the speed of light. And I solve for my frequency. So that gives me my first part of my answer. And then they wanted the energy. So I have my frequency now. H is constant. Plug those 2 values in and solve for E. So really not hard if you know the equations. Another example problem, they want the wavelength and the energy. So this time wavelength and energy given a frequency. So instead I'm plugging frequency in with speed of light, solving for wavelength. Over here, that gives me my wavelength. Then I can take that wavelength and use it. Actually, I don't even need the wavelength. I need frequency, and they already gave me frequency. So I get to plug my frequency straight in here, my Planck constant in, and solve. Just watch your units. Okay, notice in Planck's constant, it's in seconds. So when you come down here to plug in your units, you need to make sure that this one was, your frequency was given in seconds. Otherwise, you'd have to do a little conversion. Okay, so pretty straightforward equations, just a matter of knowing it. Make sure you know this fact right here. I don't know how to make a big deal about it. I'll wave my mouse around. So make sure you know this fact right here, that wavelength and frequency are inversely proportional, because that could very easily be a conceptual question.